Dear all participants, it is my pleasure to introduce Go Tokumitsu, a second-year master student in the Graduate School of Science of the University of Osaka, where he is supervised by Professor Koji Yano. His research lies in the field of probability theory, with particular emphasis on elephant random walks and martingale limit theorems. He will proceed to the PhD program in April 2026 to further pursue his research in this area. Please join me in warmly welcoming Go today. He will present a talk entitled Limit Theorems for the Dynamic Elephant Random Walk. And please, you can start.
Okay. Thank you for the introduction. My name is Go Tokumitsu from the University of Osaka, master's student in the second year. Professor Agage, thank you very much for inviting me to this webinar. English is not my first language, so thank you in advance for your understanding. Now, today I talk about limit theorems for the dynamic elephant random walk. The outline of this talk is as follows. First, I will introduce the elephant random walk. Second, I will talk about the dynamic elephant random walk. Finally, I will talk about future work. Let me introduce the definition of the elephant random walk. The elephant random walk is a stochastic process introduced by Schutz and Trim in 2004. Let S0 equal 0. The first step, x1, is defined as follows. x1 equals plus 1 with probability q, and minus 1 with probability minus q. For n greater than or equal to 1, let un be a random variable uniformly distributed on the set 1 to the n plus 1th increment xn plus 1 is defined as follows. It equals xun with probability p and minus xun with probability 1 minus p, where all the random choices are assumed to be independent. The position of the walk at time n plus 1 is given by Sn plus xn plus 1. The stochastic process Sn defined in is called the elephant random walk, ERW. Schutz and Trimper showed that the elephant random walk exhibits a phase transition and anomalous distribution. The second moment E of Sn squared behaves as follows. There exists a constant Cp times n if p is less than 3/4. This is the diffusive case. It is n log n if p equals 3/4. This is a critical case. There exists a constant Cp times n to the power 4p minus 2 if P is greater than 3/4. This is a diffusive case. Here, where xn is asymptotic to yn, means that xn by yn converges to 1 as n goes to infinity. Although the elephant walk may look like a non-Markovian process because it remembers its entire past, it is actually a homogeneous Markov chain. Indeed, the conditional probability Sn plus 1 equals Sn plus or minus 1 given x1 up to xn is equal to 1/2 plus minus p minus 1/2 times n over n. This implies the conditional probability given S0 up to Sn is equals to the conditional probability given only Sn. Okay? Next, I will introduce the limit theorems for the elephant random walk. These results were proved by Coletti, Schutz, Berg, and Kubota and Takei, depending on the regime. The behavior depends on the parameter P, and there are 3 different regimes. First, when P is less than 3/4, Sn divided by square root n converges in distribution to a normal distribution. Moreover, the LIL also holds. Next, when P equals 3/4, the normalization changes to square root n log n. Again, we obtain convergence to a normal distribution and a corresponding LIL. Finally, when P is greater than 3/4, Sn divided by n to the power 2p minus 1 converges almost surely to a non-degenerate random variable L. Moreover, if we subtract the random drift n to the power 2p minus 1 times L, the CLT still holds. Okay. Next, I will introduce the functional central theorems for the elephant random walk proved by Bauer and Bertman. Again, the behavior depends on P. First, when P is less than 3/4, the process SNT bracket divided by square root n converges in distribution in d of 0 to infinity to a R-valued centered Gaussian process. Covariance as follows. Next, when P equals 3/4, we consider a different time scaling. After the normalization by square root n to the t times log n, the process converges to a standard motion. However, in the superdiffusive regime, a functional central limit theorem for the elephant random itself is not available. Now, let me introduce the dynamic elephant random walk introduced by Coletti, Lima, Gava, Luiz in 2020. The dynamic elephant random walk, DERW, is a z-valued stochastic process, Sn, that satisfies the following conditions. First, S0 equals 0, and the increment xn, defined as Sn minus Sn minus 1, takes values plus or minus 1. Second, the expression of x1 depends on two parameters, alpha 1 and beta 1. Third, conditional expectation of xn plus 1 given the past has two parts. The first part is proportional to Sn over n, similar to the elephant random walk. Second part is an additional drift term depending on alpha n plus 1 and beta n plus 1. Here, P and Q are in the interval 0 to 1. Alpha n, beta n are sequences in 0 to 1. And Fnx is the sigma field generated by first increment. The above definition does not immediately show how the dynamic elephant walk moves. So now I will explain how to define the increment xn so that these conditions are satisfied.
And alpha n and beta n are two deterministic sequences, not random. The
Yes,
sequence.
deterministic sequence.
Okay. Thank you.
Thank you. Concretely, each increment xn is either the elephant random walk increment with probability alpha n or time-inhomogeneous random walk increment with probability 1 minus alpha n. Each increment xn is equal to yn with probability alpha n. Xn is equal to Zn, where Zn follows the definition R beta n. That is Zn equals plus 1 with probability beta n and minus 1 with probability 1 minus beta n. So Zn can be regarded as the increment of a time-inhomogeneous random walk with steps plus or minus 1. So essentially, the dynamic elephant random walk can be regarded as a mixture of the elephant random walk and a time-inhomogeneous random walk. Here, I would like to emphasize an important point. Even when the time-inhomogeneous random walk increment is chosen, the dynamic elephant random walk still keeps memory of it. What does this mean? Suppose that at step n, Zn is selected. Then at step n plus 1, yn plus 1 is selected. At that time, there is a stage where we choose uniformly from one of the past increments up to step n. And importantly,
Sorry, I have a question.
okay.
So in this model, if alpha equals 1, 0, 0, constant 0, we have the classical elephant random walk. And if alpha is constant equal 1, we have the classical random walk.
Yes, if alpha n is equal 1,
Okay.
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 Yes.
And at first you define the two processes yn and zn, the elephant random walk and the random walk, and after you construct your new process xn, sn. Is right? You consider two
Okay.
processes,
Yes.
y and z, and after, via the relation point 3 here, you construct the process xn.
Yes.
I mean that yn and zn are already defined. And the second step is to define, to construct the new process xn. And so the process sn. Okay. It's clear for me. Thank you.
Thank you.
Thank you.
Okay. And importantly, Zn is included among those. Sorry. Suppose that at step n, Zn is selected, then at step n plus 1, yn plus is selected. At that time, there is a stage where we choose uniformly from one of the past increments up to n. And importantly, Zn included among those candidates. The dynamic elephant random walk is not simply a mixture of an elephant random walk and a time-inhomogeneous random walk. Rather, they are mixed together in a non-trivial way. As alpha n denotes the proportion of the elephant random walk, we call it the elephant component. And we call beta n the memoryless component. From now on, I will refer to them as the elephant component and the memoryless component. We are interested in limit theorems arising from the mixture of the elephant random walk and a time-inhomogeneous random walk. The dynamic elephant random walk is a highly general model. If alpha n equal 1, then we recover the elephant random walk. If beta n is between 1/2 and 1 and p equal 1, when we obtain the studied by Shozawa in 2022. If alpha n is alpha, beta n is between 1/2 and 1, and p equal 1, then we obtain the model of Kubota and K 2019. First, let me introduce two quantities. We define small n and capital L squared as follows. These quantities appear many times later. However, you do not need to remember their exact forms. Each time they appear, I will write them again at the top of the slide. So please just follow the results. Now, I will present the CLT and the LIA for the dynamic elephant random walk proved by the and co-authors in 2020. Suppose one of the following four conditions holds. Uh, to, あー、then the four condition holds. Then the following assertion hold. First, we have the CLT. After proper normalization by small n, capital N, the central process converges in distribution to the normal distribution. Second, we have the LIL. Among conditions, second one is particularly interesting. So let me explain it more carefully. The second condition is 3/4 less than p less than 1 and 0 less than the elephant land component less than over 1 over 4p minus 2. When p greater than 3/4, the elephant random walk itself, the CLT and the LIL do not hold. On the other hand, if beta n is equals to 0 or 1, then the time-inhomogeneous random walk becomes trivial. In this, the increment is always -1 or always +1. So clearly, the CLT and the L do not hold for that process either. However, in the second condition, there is no restriction on beta n. Therefore, this condition includes the situation where we mix two models for which the CLT and the LIL do not hold. And yet, after mixing them, the CLT and the LIL actually do hold. We believe that this phenomenon occurs because the ERW and the time-inhomogeneous random walk are not simply mixed together, but rather they are mixed in a more complicated way. First, recall the definition. First, recall the definition of small n. Now, we present another limit theorem for the DER proved by Coletti and co-authors in 2020. Suppose that P is strictly larger than 3/4 and the elephant component is strictly larger than 1 over -2. Then, after normalization by small n, the central process converges almost surely and in L2 to a non-degenerate random variable m. Then this guy converges to 0. The dynamic elephant random walk has a critical point at 1 over 4p minus 2, which is related to the elephant component, and another critical point at p equals 3/4. The fluctuation limit in this case is stated in the next theorem. Now, let me present our main result. First, recall the definitions of small n and capital N squared. Suppose one of the following two conditions holds. Condition 1, 3/4 less than p less than 1, and the elephant component is strictly larger than 1 over p minus 2. Condition 2, p equal 1, 1 over 4p minus 2 is the elephant component strictly less than 1, and we put a technical condition on n. Then the following assertion hold. First, we obtain the CLT. After subtracting the random drift, small a and m, and normalizing by this guy, the distribution converges to the normal distribution. Second, we obtain LIL. Now let me comment on condition 2. When P for the ERW itself, such as CLT and LIL, do not hold. However, our says that as soon as we mix in even a small portion of the time-inhomogeneous random walk, these limit theorems do hold. Let me explain the novelty of our result by introducing some related previous results. Now, let me introduce the previous result. Kubota and Takei in 2019. Here, alpha n is constant. Beta is between 1/2 and 1. Epsilon n equal to beta n minus 1 and p equal 1. Suppose that epsilon n converges to epsilon, where epsilon is between 0 and 1/2 is less than alpha, which is less than 1. Then the following CLT and LIL hold. First, subtracting the random drift small a and m, and normalizing by square root of n, we obtain convergence in distribution to normal distribution. Second, the corresponding LI holds. Compared with our main result, this result assumes the convergence of alpha n and beta n. In contrast, our result does not require any convergence assumption. Moreover, our main result includes this result as a special case. Now, let me introduce another related result due to Shiozawa in 2022. Here, we again assume that p equal 1 and beta n is between 1/2 and 1, with epsilon n equal 2 beta n minus 1. We also define bn squared as the sum of 1 over ak squared. Suppose that epsilon n converges to epsilon, where epsilon is between 0 and 1. Suppose none of the following two conditions holds. Holds. Then the following as hold. In comparison with our result, Shiozawa also assumes convergence of alpha n and epsilon n. Moreover, our main result includes this result as a special case. Here, small n and capital N are defined as before. Let capital Mn be the L2 martingale defined by Sn minus its expectation divided by small n. We define this martingale difference. We define small Sn squared as the tail sum of the expected squared martingale differences. Under the assumption of our main result, we can verify that the limit width of the value of xn is strictly positive. Let us denote this property by condition star. Now, let me briefly explain the outline of the proof. To prove the results, we apply the CLT and LIL for the tail sum of martingale differences. I have underlined the conditions we need to show. First, by SLLN and condition star, we have small Sn plus 1 squared is asymptotically equivalent to this guy. Second, by condition star, this asymptotic relation and the martingale convergence theorem, we have the normalized tail sum of the squared martingale difference converges to 1. Third, by condition star, this asymptotic relation, we have this series is finite. Thus, we have the Lindbergh condition. Thus, we obtain the CLT of main result. Finally, these two series are finite. This series is finite. Okay. Thus, we obtain the LIL of our main result. Let me now state the functional central limit theorem for the dynamic elephant random walk. We assume that alpha n converges to alpha and beta n converges to beta, and suppose one of the following conditions. Then the following functional central limit theorem hold. Where Wt is a R-valued centered Gaussian process. Covariance as follows. Recall that the FD fails for the elephant random walk when P is strictly greater than 3/4. It also fails for time-inhomogeneous random walk when beta n is 0 or 1. Therefore, condition 3 implies a surprising result by mixing two models that do not satisfy the FCLT. Surprisingly, the FCLT holds. Moving onto the critical case. We have another functional central limit theorem. Here, we assume that the elephant component alpha n is constantly equal to its critical value, 1 over 4p minus 2. And beta n converges to beta. Suppose one of the following two conditions holds. Condition 1, p is between 3/4 and 1. Condition 2, p equal 1 and beta n is between 0 and 1. Then the following functional central limit theorem hold, where t is a standard planar motion. Okay. Condition 1 implies that by mixing two models that do not satisfy the FCLT, the FCLT actually holds. Now let me move on to the preparation for the proof of the FCLT. First, we recall the definition of a slowly varying sequence. As defined in this block, a positive sequence Ln is slowly varying if this converges to 1 for any positive t. Under the assumption alpha n converges to alpha, beta n converges to beta, we can extract a varying sequence Ln such that small n is asymptotically equivalent to I. Finally, we have the strong law of large numbers for the dynamic elephant random walk. Assume that alpha n converges alpha and beta n converges beta and p times less than 1. Then Sn over n converges almost surely to this deterministic constant. We will use this SLLN to estimate the quadratic equation of the martingale in the next step. Now let me briefly explain the main steps of the proof. In step 1, by applying the angle of large numbers and Karamata's theorem, we estimate the covariance. It is asymptotically equivalent to this ratio, which converts to t to the power of 1 minus 2 alpha times 2p minus 1. Let us denote this limit function by phi of t. In step 2, we briefly the Lindeberg condition, showing that this truncated second moment goes to 0. This check is easy. In step 3, up the martingale facility by Duret and Resnick, we deduce that the normalized process converges to a planar motion composed with the time change phi of t. Finally, in step 4, by evaluating the asymptotic behavior of the normalizing constants, we obtain the desired FCLT. The limit process Wt is exactly given by this explicit form. Okay. Finally, I would like to briefly discuss our future work. Please note that here we are stepping back from the DRW and returning to the standard elephant random walk. The following theory is a recent result of mine. Let Sn be the Sn be the superdiffusive elephant random walk. Then the following joint convergence holds. Where y is an arbitrary f measurable random variable, and where b is independent y. In particular, we may take y equal L. Let me explain why we take y to be L. If we divide this process by n to the power 2p minus 1, it converges L minus L, that is 0. This means our FCLT captures the fluctuation originating from L. By establishing the joint convergence y equal L, we can show that these fluctuations do not interfere with the limit L. Based on this result, our next goal is to obtain the variation bound for the following CL. These are the references. Thank you very much for your attention.
Thank you, Go, for this talk and for this nice topic. Are there some questions, please? I have a question about the model, about the step xn. Xn here has a size equal 1, because xn equals 1 or minus 1. Can I generalize this model for xn having random step size? We replace minus or plus 1 by any random variable. We impose some conditions that have finite moments of order 2, for example. Can us obtain similar results with this generalization?
Step size minus 1 or plus 1.
Yes,
Yes.
Can be any random variable, can be ln, some random variable having finite moments. Okay, I think that your model here can be extended to this case. In slide 10, please, if you can go to slide 10. Okay, the random variable m, you told that m is non-degenerate. It is Gaussian m. Can us have n Gaussian? Gaussian. Are you sure that it is not Gaussian, or can be Gaussian or you don't know?
I don't know. But I believe that M is not Gaussian.
Okay. I think so. That must be non-Gaussian. Slide 17. In your theorem, slide 17. Okay. Here for the SLLN, P must be not equal to 1/2, no? P must be not equal to 1/2 or not equal to 1, because why I think that P must be not equal to 1/2, because if P equal to 1/2, the elephant random walk Yn is will be a standard random walk, and the n is a standard random walk, and so Sn divided by n must goes to 0, not to some non-zero constant.
I see.
Okay. We can discuss this point maybe later. The last question, please. Last question, slide 19. I don't understand here why you introduce the random the random variable y. What is the utility of y here?
Okay. This converges L minus L. This fluctuation depend on L.だから、by this joint convergence, when f equal L, FCLT do not interfere with the limit L. Okay.
Okay. Yes. Okay. Thank you. Are there some other questions, please?
Dr. Rafiq.
Yes, please. Yes, Maha.
I have a question.
Yes, please.
Thank you, Gao, for this nice work. Please, I have one or two questions. In page 7, for example, in page 7, what is, I don't understand the difference between Yn and Zn. Can you explain another time, please? What is the difference between increment of the elephant random walk and increment of a time inhomogeneous random walk? What is the difference between Yn and Zn?
What difference? Yn is increment of the elephant random walk. So Yn concludes the memory. But on the other hand, Zn ZN, don't conclude the memory.
Okay.
Okay.
Yeah, thank you. Another question, please. It possible to study our model in dimension 2 and generalize with the high dimension?
なるほど。うーん。うーん。
Yes, I think sure. Yes.
Sorry. Sorry, I don't know.
Okay, thank you very much.
Thank
Thank
you.
you. Thank you, Dr. Mohammed, for your questions. Other questions, please? Joe, I know that right now you have some difficulty expressing yourself in English, but despite that, you presented your work well, and I believe you achieved good results. I thank you very much for this nice talk and nice topic, and see you at the end of this month with another talk. Thank you, Joe. Thank you.
Thank you.